So next up is Amanda Quadling. So Amanda is the Director of Materials Research at UKAEA. She's really been very much a force driving the roadmap around materials for fusion, and we'll hear more about that this afternoon, maybe a little bit today, I'm not sure, this morning. But that's really, I think, helped develop partnerships across a whole range of different material stakeholders in the whole part of the supply chain. And there's some really huge challenges there that we're all well aware of in fusion. Prior to joining UKAEA, she was technical director for M&I, actually further north, near to actually Manchester, and created a new product incubator there in collaborations with Graphene Engineering Innovation Centre. Some of those who've walked from the station will have gone past that centre, halfway between here and Piccadilly. And they're great, these things. You learn new stuff. So I didn't realise that in 1919 you were named the 10th in the Financial Times most influential women in UK engineering. So there you go. So the stage is yours, Amanda.
Dave, thank you very much. Folks, good morning. It's still just about morning, and this is the moment where you're sort of mid-session and everybody needs to take a deep breath, and hopefully I can pace to keep your attention. It's a brief sortie into fusion, and for brevity, I therefore will not go into the fundamentals of fusion. It's such a growing area of interest that if you go searching online, you will find a considerable body of information, both in the science and the application, so I do encourage you to do that. Where this becomes relevant to Royce today is because Royce was the first platform that provided us an opportunity to bring the community together across the UK 2 years ago, industry as well as academia, to talk about how we move from a science to an engineered reality. And you heard this morning, we're all about translation these days for the sake of UK Inc., and in order to make sure we have a future for our society. So it really is a moonshot science, this one. And the first picture up there today is from our MRF, our Materials Research Facility at Culham campus, just south in Oxfordshire. But I want to emphasize that this is a UK fusion materials roadmap I'm going to talk about today, but the spillover should be collaboration internationally, and the impact should be outputs internationally. If we're going to create a power plant and generate actual fusion energy, we've got to start to think about the engineering challenges in terms of the materials. And so this mountain represents the fact that Britain is on a path over the next 10 years to put the concept in place, and in the 2030s hopes to build a prototype power plant. Some of you will have seen in the press already that in South Nottinghamshire, we've got a site. It's been purchased and already the build prep starts. So this is real, it's not just conceptual, and the long lead time items will be ordered from around 2028, which doesn't give us a lot of time when we talk about materials, development and qualification. The mountain means we're climbing from all sides, the challenges, and the challenges as you see them there are the fusion challenges rather than the materials challenges. So we've got to confine a plasma, which means we've got to put it under pressure and temperature in order to be able to fuse atoms, push them together, the opposite of fission where we split them. And when we confine them, they've got to be kept safe in some space. And we use in Britain at the moment mostly a magnetic cage. So it's magnetic confinement that the technology is focused on. We will talk in the upcoming session this afternoon about whether we should start to concentrate a bit more on other forms of fusion and confinement. But for now, let's talk about our British power plant as a good focal point, and the fact that we need to get that confinement up in Tesla regions of 8 or more magnetic field, and that we've got to get the energy gain out, and after that cope with the fact that there's an intense heat that must be dissipated. Because we're building for regulators and investors, there's an assurance piece that goes on here in terms of making the plant availability and cost and safety more certain. And finally, we have a social license in which we must operate. This is nuclear space, and we've got to make sure that we're in safe space. So 2 years ago, we made the roadmap look like this. I'm going to put up 5 themes. We tried to be complementary to other efforts around the world. So Europe had already been at this game for a decade, and they talked a lot about the first wall of the device, and they had talked about the structural materials, and they talked about the heat dissipation materials. What they hadn't spent a lot of time talking about were the magnets. And so the first theme in our roadmap became, what do we do about the new rare earth tapes, the high temperature superconducting tapes that might allow us better magnetic fields. And can we think more about the materials science in that domain? If you move from science into power plant, you go from, this is a nice reactor or device we're thinking about, to the fact that there has to be a fuel cycle and it has to be sustainable. There are inventories, there's mass balance that has to be accounted for. And therefore, how do we boost the breeding of the tritium, which is the primary fuel? And also, once we have that, how do we block it from then permeating through the plant as a danger, as a radiolytic hazard? So boost and block in the tritium space. And finally, again, if you move from science into engineered reality and into power plants, you want thermal headroom to be able to feed your turbines that heat. And so you need further structural capability, up temperature, beyond what in the nuclear domain, fission and fusion, we can manage at the moment at around 550. And then finally, this piece of assurance. Irradiating materials, and we don't have a test reactor in this country at the 14 MeV and the high fluxes that we need that eventually will be the reality in a tokamak-based power plant. So we've got to do proxy irradiations around the world, and locally we do proton and self-ion irradiations. And then we've got to take the data from the irradiated samples and feed that into modeling. And there's the process flow across the piece, because we're going to be doing a lot of extrapolating going forward in order to predict evolution of the materials in the application and the failure routes at the end of application. And finally, if we can get ourselves to some better materials, if we can optimize them by reducing the elemental palettes, then we take down the degree of activation, we reduce the level of waste classification for these nuclear materials. So those were the original pillars, and they were the right ones to choose 2 years ago, and we've done a lot of work since then. So the next couple of slides are a quick romp through what the UKAEA has driven to show that we used the roadmap, but many of you represented in the room have been involved. And it's that community involvement that is going to make this a programmatic success to deliver something out the other end, an application. So this afternoon, we'll talk about extending those 5 themes and putting others in that have come to the fore more recently. Lova loca, loss of vacuum, loss of coolant. How do we deal with real situations of oxidation and corrosion? And what do we think about things like the fuel inventory, the lockup, the retention and release of fuels? There is more to be done in the version 2 2024. So across the top of each of these slides, the 5 themes, just to keep everything in context. And when we talk about the magnets, we've been looking at REBCO, the rare earth, barium, copper oxides, those tapes that are now very good at producing high Tesla magnetic fields. They run with a critical temperature and current, and if you move either side of it, you lose the optimal superconducting behavior of these materials. And so some of our first work has been proxy irradiations using oxygen to get ourselves to the graph you see on the left-hand side and zooming in to the dotted line area to see if once irradiated, we lose that critical current. And the early results back suggest we don't. And because we're nervous about the magnets, they are extremely expensive, about 1/3 the price of the entire plant. And because globally the supply is very limited, that's an important result. We know that the tape suppliers are numbered in single digits globally, and they are going to need quality assurance on the existing tapes. And so the picture on the right is a little snapshot of approximately £9 million proposal for a test center for irradiated magnet tape. And we've been working on that for 2 years. We're halfway through that funding, and we believe we can deliver that as a proposal next year to be built within 24 months. That will give Britain a unique, a world-first capability in irradiated tape analysis that allows the quality assurance on these REBCOs, which we need for the high Tesla fields. If we talk about the REBCO tape as a material, it is crystallographically quite complex, the actual active component in the tape. And when neutrons impinge on the lattice in the tape, they are going to have different effects depending on the direction of impingement. And therefore our models have started to look at the threshold energies which displace the atoms in the lattice and what the directionality does for the damage in the tape, because the tape is orientated within different magnetic fields inside a tokamak. And so always on these slides for reference, some of the folks involved, and in this instance it's Lancaster University that are helping us with that directionality in the lattice. If I move on to tritium for a moment now, the fuel, and we talk about the fact that the first wall generally will be tungsten. It's the only thing that can withstand the temperatures. And you've read in the press perhaps 150 million degrees Celsius. That is indeed the temperature of the plasma. It does not touch the walls of the tokamak device. It is hung in suspension or contained in suspension by the magnetic cage. But the walls will see the odd solar flare, if you like, and they will see 3,000 degrees Celsius. So tungsten it is, also because it's transparent enough to the neutrons to allow them through into a breeding area behind that first wall or on that first wall, and also because they have, or there is enough density in tungsten to cope with the moderating angle of the neutron transport. There's another dimension, trickier, which is that eventually the plasma does erode that first wall, and whatever you release into the plasma will poison the plasma and affect its ability to confine and to generate a fusion environment. And so there are very few elements that allow us all of those things: the temperature resilience, the non-poisoning of the plasma, the transparency, and the moderation. So tungsten becomes almost predetermined. Our game is not so much about down selection as it is predetermination in many instances. And what we've got here is some finely grained tungsten, and the tritium, or its precursor fuel, it's easier to work with deuterium, has been locked in a previous experiment, and now we want to know, where is the deuterium sitting? What are the mechanisms and the traps that hold the fuel in the first wall, and how are we going to need to release it? What kind of energies to release? And so those are atom probe tips that were created by one of our researchers. She's here today, Hazel Gardner. You can chat to her during tea if you want to know more, but her early work is showing that we can see segregation of the deuterium to the grain boundaries, and we can see specific alignment between the deuterium as fuel and some of the oxides that are being created by that first wall in the tungsten. And so the slide here on the right-hand side graph shows you that the tungsten does oxidize to some extent, and it forms different species, and they have different trapping energies, and this is the important bit for the modelers. The picture on the left is a simulation we ran where we imposed some hydrogen isotopes onto a tritium first wall, and we know that the neutrons are creating vacancies and that the hydrogen and other isotopes are going into those vacancies. They're being trapped. And so when you move from hydrogen to deuterium to tritium and you move up mass, the trapping changes and the penetration of retention reduces. But at the same time, it was quite a surprise to see that you could get up to 6 of those hydrogen isotope atoms locked into a single vacancy. And so this starts to give us quantitative information towards the fuel cycle and what happens to the inventory in situ. If we move to the third of the themes and we talk about structural materials, I've talked in the past about castable structural materials for fusion, and we've got MPI represented in the room, and we've been up recently to have a look at their abilities. 6-ton castings. We can do research castings in this country around novel alloys. We've talked with Forge Masters and with Cooks and others. I'm naming names because I want to reinforce that UK Inc. still has a manufacturing base and a very strong heritage of which to work towards new supply chain in fusion as well as other applications. Here what we're trying to, or what I'm trying to present today is something that is not about cast metals, but about pressed metals or metals that can be produced in other ways. We want our defects created by the neutrons impinging on our materials to be controlled and limited. A point defect often generates a cascade, and we get dislocations, we get runs of defect through the materials, and that destroys their mechanical properties. If we want to stop that, we've got to put some kind of blocker in the path, and the defects sinks that we choose are nanodispersants. If we can create a secondary phase, whether it's inter or intragranularly in our material, then the dislocations run to that point and the energy is sunk, and we stop the propagation of the defect. So oxide dispersion strengthened steels have oxide nanodispersants to stop the run of those dislocations. So we've been experimenting with hot isostatic pressing, with additive manufacturing, with field-assisted sintering, and we see different things coming out. So in the little micrographs across the center there, the field-assisted sintering is giving us fantastic dispersion of the nanodispersoids, the lower candy-colored picture, but there's a lot of porosity, and that porosity is not helping with the mechanical properties. So early attempts there, not going well. The last of the 5 micrographs shows you picture-perfect microstructure. We've got no microporosity there, or none to speak of, and that's a beautiful microstructure from a mechanical engineering perspective. But unfortunately, if you look at the lower right-hand side, you'll see we've got one or two blobby big yttrium-based nanodispersoids, and we're not getting the beautiful dissemination that we need for a proper resilient neutron structure or neutron resilient structure. So it still looks to be hot isostatic pressing as the best. It's expensive. It's 200 megapascal in terms of the pressures, as opposed to maybe 50 megapascal in the field-assisted space. And so there is a cost deficit there. But we proceed in this space because ODS steels are one of the only materials that might get us up over 550 in the structural space in a working plant. They're interesting under microscope because they have very bimodal grain sizes, and the smaller the grain size, the better from a fracture toughness point of view, but a worse case for us in terms of creep resilience. And therefore, we don't quite know what to do about this. The more anarchic the microstructure in many ways, the better for neutron resilience. But there has to be a degree of repeatability, reproducibility in the manufacture going forward. So some of our work takes us into looking at things like grain orientation studies, the last picture on the right, where one particular cluster of the grains has got a really localized higher density of dislocations and defects. And we don't like that. We don't want local strain that makes for an uneven response in the materials, as you would know. So lots more work to be done here in fundamental science, but it's not as simple as low TRL, high TRL work. We want to be able to innovate at scale. It's the industrial scale processes that must control this microstructure so that we can use it in this applied space. And so we're moving back and forth across TRL levels, but we're doing fundamental work for application. Some of the steels that we've produced over the last couple of years, we've done with Sheffield Forge Masters, with the National Nuclear Labs, with the University of Sheffield, increasingly with the University of Swansea. Got a lot of folks involved in this work and creating a variety of different alloys. One of them, on the left-hand side, the red circle nib, is a nuclear innovation program output. That's a 60-ton ingot we've managed to create in this country. And we've taken some of that material now and sent it off to Oak Ridge in America, National Lab, where we've set up a £3 million 5-year irradiation campaign. So that's a British novel fusion steel that we're testing for the first time, irradiating it up to 5 to 8 dPa, displacements per atom damage, and we'll bring that steel back to Britain, to Cullum and other places, and we'll look at what that irradiation damage looks like. Ringed on the right-hand side, there's CNA, complex nanostructured alloy. That's something we generated with Swansea, a new UK-based fusion novel steel, and that's gone for irradiation. The picture on the right-hand side, acknowledgements to Oak Ridge National Lab, is the reactor, HIFA, the high-flux isotope reactor. And the tensile bars that we're using are mini tensile bars. It's very small amounts of this material that we need in order to irradiate and then bring back and have a look at. What happens if we take those mini tensile bars and we do a little bit of an experiment on a SEM, a scanning electron microscope? You've got a tiny bit of data from a tiny piece of material, and you've got a design engineer now wanting to put meter scale components into a power plant design. The only way you can do that going forward at the moment in our timeframes is through clever modeling. And this very busy slide, to whet your appetite, really boils down to the strong blue box you see running in the middle there, designed by Fundamentals. That is a purposeful play on words. Engineers design by rules, they design by analysis to date. We're going to have to do not interpolation of data, but we're going to have to do extrapolation of data. And we don't want to do it without it being physics-based. So this is why it's designed by Fundamentals. We're going to take the physics rules that dictate how the material evolves based on its crystallography and its composition under neutron bombardment. And so the first work we've done is in crystal plasticity, the plastic ways of failing rather than the brittle ways of failing. And the team, working together with Oxford and Imperial, have put together some crystal plasticity code, looking at about 4 or 5 different slip systems in one particular material, a copper chrome zirconium at this moment in time. And along with that, the little top picture on the right, they've worked on increasing the throughput rate for the models by putting better solvers together. So working on both the physics code and also the mathematical solvers. Those two things coming together need validation, and they need validation through experiment. So we're also working on, the middle section of the slide, novel ways of doing micro-cantilever testing and tiny compression and tensile tests to validate the models that we're creating. The next step down in this methodology is to see if we can't then generate a proxy three-dimensional structure, microstructure of our material. That's what you're seeing right on the bottom right there. We've done that with some Python-based bespoke code. And if we bring it all together, we should be able to start to put what we see in post-irradiated materials, things like slip bands that transgress grain boundaries, into the solver hastened three-dimensional model, and using the physics, extrapolate and predict how that material will evolve. This is world-class stuff that's going on. I'm very proud to be able to present this. And we're working with the fission community because there's work being done on Zirc alloy in the fission community along the same lines. And where we've made some inroads early on the plastic side, we're going to have to think about brittle failure. And we need orders of magnitude more effort on this particular part of the problem, this challenge going forward. And we'll be talking more about this afternoon in our session. Finally, the last of the themes there, if we think about reducing waste in nuclear, we want reduced activation, and that means tweaking some of our elements, choosing the isotopes that have shorter half-lives. And towards that, we've done some work with University College London and with Cambridge on solvent-based exchange of lithium between aqueous and organic substrates to see if we can develop enrichment in lithium and also in molybdenum. And some of the results we're just showing on the right-hand side there indicate 1.03. That's a very good segregation, in fact, relative to what's been achieved before, because the only other way of doing the lithium enrichment actually at scale cost-effectively is a process called Colex, and it's heavily based on mercury, which from an environmental point of view we don't want. So we've got to think of other ways of doing isotope enrichment. And while the lithium enrichment is not towards the waste reduction, conceptually what I'm presenting is the fact that tuning of isotopes is a field of expertise we're going to have to develop more in to do the reduced activation work. And so finally to say that from 5 pillars or themes in our roadmap, we're going to go towards a dozen. Some of the names are up there of folks who have already committed. This afternoon we'll be going into a session where we're going to start to talk about a working group for the first half of next year. We're going to talk about what the scope of that roadmap actually is in its next iteration. Do we go beyond magnetic confinement? We'll be thinking about push and pull, opportunities to support STEP as a British endeavour, but also where else can we help in the world? Do we want to bring in fission learnings better, and how do we do that? And we'll put our plan together. And so for those of you who are joining us this afternoon, I look forward to seeing more of you talking more about what I've presented here. But thank you, Royce, for the support always.
We've had a few questions come in, some of which perhaps you'll take this afternoon, because I think they'll be relevant. But there's one which is a sort of broader one, I think, which is quite interesting. It's a little bit about Europe. So obviously, it's really about the relationship with ITER at Cadarache, the activities there, and I guess, you know, the involvement of the UK on that international stage, but also what the impact of things like Horizon are for you as an organisation.
2 bits to that question, so let me go with ITER and Cadarache to begin with. ITER is a phenomenal experiment. It's the world's biggest science experiment at the moment, £20 billion, and of course it will grow with the world's economy growing. It's about 70–80% built. I went and saw it about 6 weeks ago. And it has hit challenges, materials challenges as much as anything else. And those are learnings, and this is why you build. You build to learn. It will come live in the 2030s. It is not a power plant. It is the device that is aiming to generate net energy, more energy out than in. We are part of that. And some of the work that we've been doing at Culham on the Joint European Torus jet, which has been running for 40 years and closes now at the end of this year its operations, will help with understanding things like first wall and the generation of dust. Dust, it was mentioned earlier today, is very dangerous generally in safety in applications. So some of the quantitative information we've now got on generation of dust from a first wall at JET will translate directly into the work that's got to be done at ITER in terms of controlling dust generation there. It's just one example of how our work here helps towards ITER. Your second part of your question
was about Horizon and the impact
about Horizon. What I'd say is that we have multiple conduits between UK and Europe, and Fusion specific is Euratom rather than Horizon, and Euratom Association at this moment is in negotiation. So we hope that once Horizon negotiations clarify, then we will know where we stand with Euratom. We stand ready to put in a plan B, an alternative strategy, if Euratom Association does not proceed.
Great, thanks. I mean, Fusion's always been such an international collaboration. I think that's a really interesting topic.
Dave, maybe then I'd add and just say at this moment in time, we had Japanese delegations visiting us last week. We've got a South Korean delegation visiting us next month. We are in constant communication on a bilateral with the US. It is, as you say, a truly international field at this moment in time.
Okay, great. And there are some other questions, but I think I'll leave those, and hopefully the people that asked them, I'm sorry I didn't get to bring them up, but you can ask them later this afternoon.